Hello everyone, I'm Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. We will now be going over the contents of week 10. Yes, it will help you in solving your assignment, which is due tomorrow. We'll just go over all the content and then we'll move on to week 10 content. Okay. So in the weeks preceding to week 8, we had discussed static stability in the longitudinal, directional, and lateral sense. So static stability's conclusion was that we require Cm alpha, the derivatives that contribute towards stability, right? So you have Cm alpha less than 0 for longitudinal stability, Cn beta greater than 0 for directional stability, and Cl beta less than 0 for lateral stability. Now the major contributors towards these stabilities. So for longitudinal case, you have horizontal tail. Horizontal tail is what provides the most static longitudinal stability. So it is the most negative component in Cm alpha. Similarly, for the directional sense, you have the vertical tail with the rudder. This is what gives you the most positive component in the Cn beta terms. Vertical tail contributes most to the Cn beta. And for the lateral case, you have these three terms. You have vertical tail, high wing, and dihedral angle. We had discussed this previously, but I'll go over it again. The high wing, why it gives you stability and why the low wing does it. So high wing, when it is rolling, it banks towards the right, you have this configuration. The oncoming wind hits on the lower surface of the wing and produces a restoring moment, which is why it produces stability. So it contributes towards stability. Now, if for the same rolling, you have a low wing configuration. You have, and it rolls again towards the right. The oncoming velocity would push against the upper surface, and you have a further deteriorating component of moment. It has no restoring term. Okay, so the low wing configuration is not stable in the lateral sense. Now, how do you make it stable? You introduce a small dihedral angle. So, what is a dihedral angle? Your initial low wing was like this. Now you introduce a dihedral angle. That is this. And as derived in the lectures, these contribute towards lateral stability. Okay. So this is the conclusion of your static stability. These are the three derivatives that tell you whether your aircraft is stable, whether your aircraft is statically stable in the longitudinal sense, directional sense, and lateral sense. We then moved on to dynamic stability. We started with a point mass. Point mass in a 2D system, in a 2D frame, in a 2D coordinate system. The point mass system is defined by these four equations of motion. But the first equation shows you v dot, how the velocity varies. Then it shows you gamma dot. Then the translational components, how it varies in the x direction and how it varies in the y direction. Okay, so these are the four dynamic components that show you how, these are the four equations of motion that show you how the point mass moves in a 2D coordinate system. Okay. We then moved on to aircrafts. So we moved from point mass system to an aircraft. So what comes is the aerodynamic parameters. Aerodynamic parameters are CL and CM for longitudinal case. Okay. Till now, how did we approximate CL? We took CL as, we linearly assumed CL to be varying as CL naught plus CL alpha into alpha and CL delta E into delta E. Similarly, you had CM naught and CM alpha into alpha and CM delta E into delta E. Now, when the dynamic stability comes into play, when you do the dynamic analysis, you have a time component that comes in. When the time component comes in, you have two new terms, that is pitch rate Q, and rate of change of angle of attack alpha dot. Okay, so you have these two new terms that are added here. Ideally, you should have added it as CLQ into Q, right? But what happens is this CL is a non-dimensional term. So the final thing should have no dimension. CL naught has no dimension. CL alpha has no dimension. Alpha is dimensionless. It's radian. It's dimensionless. CL delta E again dimensionless. But when you take CLQ into Q, Q is radian per second. It is pitch rate. Okay, it's the rate of change of pitch per second. So it has radian per second and it is not non-dimensional. How do we non-dimensionalize it? So like we need to get your final value as non-dimensional. So we need to non-dimensionalize it. How do you non-dimensionalize it? You multiply C and divide by 2B. and you define your CLQ also accordingly. How is CLQ defined? CLQ is dou CL by dou QC by 2V. Now this 2 is just a matter of convention. You can also avoid it. We are following this convention. Similarly, you define C and Q. C and Q is dou CM by dou QC by 2V. This CLQ, C and Q are defined such. Again, you follow the same process for alpha dot, because alpha dot again has dimensions of radian per second. It is not non-dimensional. You non-dimensionalize it by taking alpha dot C2V, alpha dot into C by 2V. And again, you define your CL alpha dot as dou CL by dou alpha dot C by 2V and CM alpha dot as dou CM dou alpha dot C by 2V. Okay, so these two new terms are added into your CL and CM equations. Again, it's a linear approximation. That is what comes. Now, what happens when you introduce a pitch rate to an aircraft? When you pitch up the aircraft, pitch down the aircraft, when you have a pitch rate Q, what are the changes that we see? What we see is that the angle of attack at the tail changes. So when your aircraft, if this is your fuselage reference line and it pitches up, so if your tail was here, if your tail was here and it pitches down, so there is a change in the angle of attack that is witnessed at the tail. You have a delta alpha tail, and it is approximately equal to QLT by V. Q is the pitch rate, LT is the moment arm, that is the distance between the CG and the aerodynamic center of the tail, and V is the velocity. So it is approximately equal to QLT by V. Okay. So now when there is a change in angle of attack at the tail, there is also a production of lift. There is a change in lift. And if your tail was like this and it is subject to an angle of attack, delta alpha tail, there is a delta lift that is produced, okay, which produces a pitch down moment, delta M. Since it's pitched down, you have a negative sign here. Delta L is given by this equation and delta M is given by this equation. There is a negative sign. Now we differentiate it and we calculate the derivatives, that is CLQ and CMQ. And we've been doing this for the past 2-3 weeks. CLQ is given by this equation, CMQ is given by this equation, and you have the negative sign again. Now what we do is we compare our system to a second order spring mass damper system given by this equation. And what we can see by comparing is that, so first of all, we take the states of the spring mass system were X and X dot. So the aircraft system, it is alpha and Q. So you have alpha and Q. Alpha is analogous to X, Q is analogous to X dot. Okay, so the term that is analogous to K would be CM alpha, because you have CM alpha into alpha. So CM alpha is analogous to K. CM alpha is analogous to stiffness. CM alpha tells you how the aircraft withstands any disturbance, how it responds to any kind of disturbance that it encounters. Okay, so it's like stiffness, how the spring withstands a deflection due to a mass. It's the same thing, how the aircraft withstands any change in the alpha. So CM alpha gives you a measure of the stiffness. It's analogous to stiffness of the spring mass damper system. CMQ. So CMQ into QC by 2V, that's the term we have. Okay. So there CMQ is analogous to the damping. So how your aircraft would come back to the equilibrium after some time. So time factor comes in here. If your aircraft, okay, for the spring mass damper system, if it is perturbed to some value, how it tries to come back to equilibrium, or if it does even come back to equilibrium over time. So that is what the CMQ signifies. That is what your C in the spring mass system and CMQ in your aircraft system. It is a measure of the damping. It tells you whether your aircraft is dynamically stable. That is, if it does come back to equilibrium after some time, or if it's not dynamically stable, if it diverges. So if it goes away from the equilibrium after it's perturbed, it tells you. CMQ is that term that tells you these values, because CMQ is analogous to damping. Okay. Now we see the forces and the frames that are used for this analysis. The forces we've seen are the aerodynamic, gravitational, and propulsive. Aerodynamic are what? lift, and drag. They are by virtue of the relative velocity seen by the aircraft. Relative velocity is the velocity with which the aircraft is flying in the air, or the velocity with which the air is hitting the aircraft. Anything that's the relative velocity v. Okay. So they come by virtue of relative velocity. So lift is equal to half rho v square cl. So v, there's a v term, relative velocity. Gravitational forces are by virtue of its weight. So mg, mg sine theta, mg, those components. Okay. Propulsive forces in this case are just thrust. So the thrust that is applied on the aircraft to move it, those are the propulsive forces. Now we use two frames to perform this analysis. We use the inertial frame and the body frame. Okay. Body frame, why? Because it is easy for us to measure all of these terms in the body frame. That is the forward velocity, u, v, w, the rate of change of these components. All of this measuring in the body frame is easy because we have our instruments such that we can measure them in the body frame. But the problem arises when we use it in the equations of motion. So the equations of motion that we derived in the last class were like this. F is equal to m dvc by dt and m is dh by dt. F is force and m is the moment. So the force and moment equations, those derivatives are valid only in the inertial frame. Okay. So when we have to find out the derivative in the inertial frame and we are doing our measurements in the body frame, we need to equate those. How do we equate those? We use this. Just erase these lines. We use this vector in a rotating frame derivative formula that was derived in the previous week. So differentiation of a vector in the inertial frame is equal to the differentiation of vector in the body frame and this omega cross A term. So A is the vector here. So A is the vector. Omega is also a vector. Omega is the angular velocity represented by this. Okay, here I, J, K are the body frame. So let me just write that. I, J, and K are body frame. Given any vector, you can define it in any frame. So if I define A in the inertial frame, A vector would be AX IE plus AY JE plus AZ KE. In the body frame, it would be, let's take small x, AX IB plus AYJB plus AZKB. Now, if you differentiate this vector in the inertial frame, you have dA by dt in the inertial frame. So those terms would be dAx by dt I cap plus day by dt j cap and so on and so forth. If you take Ax and the derivative of those unit vectors are 0 because you're assuming your inertial frame to be fixed. You're assuming why? Because you've taken the earth fixed frame as your inertial frame. We can assume it to be inertial for our case because your dynamic analysis is considered, it's performed for a short duration. Okay. So your IE, JE and KE. So IE, JE and KE are fixed in time. So there is no DIE by dt. Those terms are all 0. So you have yeah. So the next term would have been dAz by dt k cap plus AX DIE by dt IE plus AY dJE by dt plus AZ dKE by dt. Now, since these frame, that is the inertial frame, that is IE, JE, KE, they are fixed in time, these terms become 0. Okay. So your final value is only these 3 terms in the inertial frame. Now, if you differentiate in body frame, you have dAx by dt IB dAy by dt JB plus dAz by dt kb. This is in body frame, okay? Plus ax dib by dt plus ay djb by dt plus az dkb by dt. Now what this gives you is dA by dt in the body frame, which is this term, plus omega cross A. Okay, so this is same as this because it's the same vector that you're differentiating. So you can write dA by dt in inertial frame. This is what is given in this equation. Now we use this equation in our force and moment equations to see how we relate the inertial frame derivatives and the body frame derivatives. So this is what we derived in the previous class, and this is in the inertial frame. This term is in the inertial frame. How do we relate it to body frame? We do the same. We apply this formula over there. So you have m dvc by dt in the body frame plus the omega cross vc term. And for moment, you have dh by dt. This is in the inertial frame. You have dh by dt in the body frame plus omega cross the vector. Okay. Now we look at the various parameters that we will be using throughout this and their components in the body frame. Now I have told you before that ijk is body frame. So the components of the force in the body frame are Fx, Fy, Fz. Similarly, components of velocity are u, v, w. Components of angular velocity are p, q, r. And moment is lmn. So I've just represented the moment vector as m because there's a pitching moment here, m. H is hx, hy, hz. Okay, these are the components in the body frame. Body frame is ijk in this case. Go to the next slide. Yeah. So for dynamic stability, we now expand these fx, fy, fz and the lmn to get these two sets of equations. Now, I have mentioned in the previous class, previous session, that is week 9, that if you differentiate this m dvc by dt in the body frame, you will have terms such as u dot, v dot, w dot. You will also have terms that are products, that is omega cross vc. You will have products of pqr and uvw. Okay. So you can see you have u dot, v dot, w dot, and you have these product terms that come due to omega cross vc. Okay, and this comes from dvc by dt, this term. And uvw, their derivatives are in the corresponding frame. So for x it is u dot, for y it is v dot, for z it is w dot. Okay. Now what are these equal to? They are equal to the sum of all the forces. What are the forces acting? You have aerodynamic, you have gravitational, and you have propulsive. Propulsive is thrust, which is Ft. Okay. Similarly, we do the analysis for the moment. That is the moment equation, Lmn. So in the previous class, that is for week 8, sir had derived hx, hy, hz terms, and they had terms involving the moment of inertia, that is ixx, iyy, ixz. Such terms were there in each of these components. Okay, so you can see that when you do the derivation in the body frame and related to the inertial frame, you have these terms that come. That is for Lmn. So these are your 6 equations. Okay, the forces and the moments. Next, we need to see the orientation of your body. How do you see the orientation? How do you measure? How do you represent orientation? Euler angle is Euler angle sequence are one of the ways in which you can represent the orientation of a body in space, in any space, in any frame. Okay. So how do we represent? It's xi, theta, phi. In that particular order, it is convention. It's a convention for aircraft orientation. So xi, theta, phi. In that particular order. Okay. It is with respect to inertial frame. So your xi is the rotation of your body with respect to z-axis of the inertial frame, with respect to ze. It is not to be confused with yaw. Yaw is the rotation of your body. So it is the orientation of the body, rotation about z-axis of the body frame. Okay, this is z-axis of the inertial frame, not the body frame. So you have xi about ze, which is not the azimuth, which is the azimuth and not the yaw. Similarly, you have theta. Theta is about y1. What is y1? So initially, your aircraft is at one place. You're rotated by xi, rotated about ZE by an angle xi. Then you have a new coordinate system, which is x1, y1, z1. Okay, you have x1, y1, z1. Z1 is same as ZE because you're rotating the initial about the ZE. Now, if you rotate about the new y1, you get theta, which is not same as pitch. Pitch is about the body frame again. So it's not pitch, it's an elevation. It is a rotation about the intermediate axis y1. Okay, it's not about the body frame. Okay, so xi and theta, not to be confused with yaw and pitch, they are azimuth and elevation respectively. Now, where do they come into play in our equations? They come into play in the gravitational components. The gravitational components are these. So they come into play here. In the previous assignment, we had discussed and I asked why xi is not featuring. So you just think about that. So these are the terms in which your Euler angles come into play. Euler angles, theta and phi. Okay, so it comes into play here and in the omega, that is PQR. So PQ omega was defined as Pi plus Qj plus Rk, where IJK are body frames. So these Euler angles come into play in the gravitational component and the PQR. They do not feature in the aerodynamic or thrust terms. Why? Can someone tell me why? Why don't these Euler angles come into play in the aerodynamic or the propulsive force terms? Can you tell me why? Can someone just tell me why they don't feature in the aerodynamic and propulsive terms? I just said that this theta, phi, xi, however, does not feature in the forces. They only come in the gravitational component. Why don't they come in the aerodynamic, this is Fa and Ft terms? Can you think about it and tell me why they don't come? So when we had defined the frames, I had said that it's easy for us to measure some terms in the, somebody has said, because of the stability axis. Not really, no, not yet. So think about it. Let me just try to help you with it. So when we had picked the frames of reference, the inertial body frame, I had said that it's easy for us to measure some terms in the body frame, and we require, in some of the terms, it's easy to measure in the inertial frame, which is why we have these two frames. So does that give you a clue on how these come? So Fa is aerodynamic force, Ft is propulsive force. In which frame are they measured? The aerodynamic and thrust, that is propulsive forces, which frame are they measured in? We have only two frames here, that's the body frame and the inertial frame. Stability axis, we have not yet come to that. So just think about this. In which frame do you think it will be measured, the aerodynamic and the thrust forces, propulsive forces? What are the aerodynamic forces? What are the aerodynamic forces? Okay, if you want to consider the stability axis, fine. Stability axis is, I haven't said that yet. Stability axis is when you orient your the axis with respect to the oncoming velocity. So if your x-axis, this is your aircraft. So this was your aircraft, and you have the x body. Are you saying something? Amod, are you okay? Okay. So this is the x of the body axis, z body, and you have y body. Okay. And when you are subject to an oncoming velocity v, we take the stability axis to aid in simplifying the equations such that your x dash is oriented with this. So you have a perpendicular to it. Perpendicular this way. Just a minute. If your YB was something like this. your y dash is like this. Okay, so this is your stability axis. The x dash and y dash are the stability axis. So even if you consider that, why are these xi, theta, phi terms not appearing in the FA and FT, in the aerodynamic and the propulsive terms? They're only appearing in the gravitational force. Why aren't they appearing in the aerodynamic and thrust? Think about it. I just said one clue is that we measure some things in the body frame, we measure some things in the inertial frame. So I think it should help you in answering this. No? I in fact said this in the previous lecture. Just think about it for a while. Of these three terms, the three forces acting on the aircraft, aerodynamic, thrust, and gravitational, I guess it's because exactly. So your aerodynamic forces and thrust forces are measured in the body frame. Your lift and drag are the aerodynamic forces. They are measured in the body frame because your velocity is also measured in the body frame. Okay. So your half rho v square, SCL, all of that is the V is in the body frame. So your FAX, FAY, FJZ are in the body frame. Then FT, FTX, FTY, FTZ are the propulsive forces, again measured in the body frame. Okay, it's easier to measure in the body frame and it is measured in the body frame, which is why the orientation of the body with respect to inertial axis doesn't come into play. Euler angle is the orientation of the body with respect to inertial axis. When you're measuring the aerodynamic and thrust forces in the body frame, the orientation does not come into play. Okay, so that is why it only appears in the gravity. The gravitational forces, the weight components will have the orientation will have an effect on those forces. Okay. Let's go to the next slide. Okay. So now we analyze for longitudinal dynamic stability. Longitudinal dynamic stability, what are the motions that come into play here? You have u dot, you have v dot. So longitudinal will be only in the xy directions, xy axis, in that plane. Okay. So x axis you have u dot, y direction you have v dot, and the rotation in that about that axis is the pitching moment. So you have q dot. Okay. So you have u dot, v dot, and q dot. These are the three equations. These are the three dynamic equations that are used to analyze the longitudinal dynamic stability. Okay. Okay. So how did we get these equations? From this case. So you take fx, you take fy, and you take the q dot equation, which is this equation. Okay, so these are the three equations that you take. So these are the three equations that you take to perform longitudinal dynamic analysis. Okay, stability analysis. These are the same three equations. Okay, I've just substituted the fg terms. This is fgx, this is fgy, and the moment in the pitching moment is the one due to aerodynamic and one due to propulsive. Okay, moment due to aerodynamic forces, moment due to propulsive forces, MA, MT. Okay, rest of the terms are the same. Now to perform this analysis, what we do, we consider this in equilibrium. Okay, what is the equilibrium for an aircraft? It is the steady state condition, cruise flight, all of these are the equilibrium conditions. So we take the small perturbation theory, which says that you act when the aircraft is at equilibrium, you perturb it. You perturb it by some small perturbation. Okay, perturb it at the equilibrium. Equilibrium in our case is steady state. Okay, so what are the terms that we perturb? We perturb u, v, w by, so u1 is the velocity component in the x direction at steady state. v1 is the velocity component in the y direction at steady state. Similarly, w1 in the z direction at steady state. So all of these terms with the subscript 1 are measured at steady state. Okay. Similarly, you have these Euler angles, terms measured in steady state, and these are the perturbing terms. You have fx, fax, fay, and faz. These are the ones measured in at steady state, and these are the perturbing terms. I should also written M moment terms. Okay. So you have MAX is MAX1 plus M, so on and so forth. Okay. These are the terms in which we introduce a small perturbation to analyze the stability, dynamic stability. So to analyze whether it will return back to your equilibrium when subject to a perturbation. Okay, so you perturb the aircraft at equilibrium and see if it comes back. Okay, now here is when the stability axis comes into play. Stability axis is chosen along the velocity direction to simplify the perturbed equations of motion. What it does is when you take an axis that is aligned along the oncoming velocity, there are no components of velocity in the y direction and the z direction, because your x axis of the stability axis is aligned with the velocity. Okay, that is one simplification. Another simplification is your aerodynamic forces. Aerodynamic forces are perpendicular to your velocity. So you have lift perpendicular to that and drag parallel to that. Again, it allows us to easily simplify the equation. Again, for thrust forces, it is again aligned to the velocity. It's more often than not aligned to the velocity. Okay. So this stability axis is chosen for our simplification purpose. That is the only reason. Okay. Once you choose those stability axis, your final perturbed equations of motions in the longitudinal case are given by these three equations. So Fx is the perturbed aerodynamic force, Fz is the perturbed aerodynamic force, M is the perturbed one. Okay, and all of the terms with subscript are measured at steady state. So theta 1, u1, all of those are steady state values. Okay. Okay. So these are the three perturbed equations of motions after your simplifications. Next slide. Okay. Now we represent. So these had three terms. This previous equation had three terms: Fx, Fz, and M. Now we see what each of these terms mean. Okay, so we take Fx and represent it this way. So again, it should have been, sorry. Yeah, it should have been dou Fxa by dou u into u. We are again non-dimensionalizing it because alpha is non-dimensional, delta E is non-dimensional. To non-dimensionalize the term, we are dividing it by u1. Similarly, even the derivative is divided by u1. Somebody has asked this question in the forum, why are we dividing it with u? How can you say that it is? It's not something that's defined. We are defining it. We are taking it such that the entire thing becomes non-dimensional. Okay. Yeah. So each of these terms, so Fx is a function. Sorry, Fx is a function of u, alpha, and delta E. Fz, the x direction, though there are terms that involve alpha dot and q, they are negligible and we are neglecting them. So in the z direction, we cannot do that. You have f that is dependent on u, alpha dot, q, delta E. Just excuse me for a moment, I'll just take some water. Similarly, the perturbed moment depends on, again, it's pitching moment, so all these terms will come into play. You cannot neglect the effect of alpha dot and q. So you have depends on u, alpha dot, q, delta E. Okay, and we take a linear approximation, and these are the equations that give that. Now we take the first equation, that is Fx, the first equation. We take the first equation and analyze the derivatives. We see what the derivatives mean. The first derivative is dou fxa by dou u by dou 1. Okay, dou u by dou u1. This is the first one. This gives us this value. Similarly, the second derivative gives you this, and third derivative gives you this. And the negative signs come into play. Why? Because your final force, if it's in the upward direction, it is in the negative z direction. So you have these negative terms that compensate for that change in the sign. Okay. Now, what is CDU? So I had mentioned how the Bragg polar changes with respect to Mach number. Okay, so you have CD, which remains constant in the subsonic region, and then it increases, and then it decreases. So this value, it increases up to Mach 1. And this is, I think, 0.6 or 0.7. So up to 0.6, your CD, this is CD, CD is 0. And then it's a positive value till Mach 1. And then it has a negative value in the supersonic region. Now CDU is analogous to CDM. So this CDM is 0 up to Mach 0.6. It is greater than 0, 0.6, less than 1. And it is less than 0 when Mach is greater than 1 in the supersonic regime. Okay. So U is nothing but velocity. So if you divide U by A, you get Mach number. So it is CDM and CDU are analogous. Okay. It has the same physical significance. That is what is CDU. CD1, what is CD1? CD1 is measured at the steady state. It is the CD, drag coefficient at steady state. CL1, similarly, lift coefficient at steady state. CD alpha. So it's a rate of the coefficient with respect to dou CD by dou alpha. Okay, that is CD alpha. CD delta E, those are those terms. Now, after substituting these derivatives into this equation, you get your U dot equation. U dot is the first equation of motion for your longitudinal dynamic analysis. So your longitudinal dynamic analysis, this is the equation. It's simply substituting all of these derivatives into your fx equation. Okay, it gives you this. Now we simplify it and write it as U dot is equal to xu u x alpha a alpha x delta e minus g theta by cos theta 1. We write this to represent finally in form of a matrix in a simplified matrix form. Okay, so this xu is nothing but this term. This entire thing is xu. This entire thing is x alpha. This entire thing is x delta e. And g cos theta 1, g cos theta 1. I repeat again the g theta 1, some ones with subscript 1 are measured at steady state value. Okay. And all of the others are the perturbed quantities. Delta E perturbed, alpha perturbed, delta E is not perturbed, alpha perturbed, U perturbed, the small u, small alpha, they're all perturbed quantities. Okay. Now we go to the next equation, that is Fz. First was Fx, now we see Fz. Now these have two more components that depend on alpha dot and Q. Okay. So this is something I should have discussed earlier. Why alpha dot? Why are we taking alpha dot and not just pitch rate? Why alpha dot? Alpha dot is because initially we had taken CL alpha, CM alpha, all of those quantities, thinking that when you change the angle of attack, it would immediately come to that angle of attack, which is not true. So when you change it, the lift builds up over some time. So the alpha varies over time. It doesn't just come statically to the next value. It builds over time. Okay, so that is one reason. Next reason is downwash, that is epsilon at the tail. What are the effects? We had discussed this. So due to the vortices, due to the finite wing, due to the end-tip vortices generated on the wing, these vortices move back towards the tail and reduce the effective angle of attack at the tail. They reduce alpha t. This again does not happen in a split second. It happens over some time. Okay, so the reduction in angle of attack at tail due to the downwash effects happen over some time. So the angle of attack alpha tail dot, there is a rate of change of angle of attack, which is why alpha dot comes into picture. It is not that significant in Fx, but it is significant in Fz and the pitching moment M. Okay, so this is why alpha dot has come. Now how it varies with alpha dot? Okay, so CL alpha dots, you have this term here. This is what tells you how your that lift coefficient varies with alpha dot. So you can see that it is dependent on your downwash. Downwash is the term that is time dependent. So when you have alpha dot, your downwash component comes into play. Okay. CLQ we have seen before. So this is CLQ. We had studied this right at the beginning of the dynamic analysis. So this CLQ comes into your FZA in this form. So this is the CLQ, and you get, where is that? Yeah, it comes here. Okay, it comes here. So to non-dimensionalize, we had done QC by 2V. In this case, we will do QC by 2U1 because everywhere we're using U1. U1 is the value at steady state. Okay, so the third derivative, this derivative is given here using CLQ. CLQ we have got from here. Okay. Okay. And now for alpha dot, you get this equation, and both of these equations, like I had mentioned previously, why is there a negative sign? There is a negative sign because your final force due to change in angle of attack at tail, your force is produced in this direction, upward direction, in the lift direction, delta L. But that is in the negative Z direction. So you have this negative sign that comes into both of these. Okay, you have the negative sign that comes into both of those equations. Fx delta E, that is similar to the Fz delta is similar to, okay, this is supposed to be Z. Okay, just excuse me for that one. It's similar to the previous case. Again, as like the previous case, substitute these derivatives into the final equation to obtain W dot. Okay, this is not omega, W dot. W dot equation. Okay, this again, you can use terms like XU, so you can use terms like ZU, Z alpha and represent. So your, this would be ZU, this would be Z alpha, this would be Z alpha dot, this would be ZQ, and this would be Z delta E. Okay, similar to the previous case. So you can write minus mg theta sine theta 1 plus ZU into U by U1 plus Z alpha into alpha plus Z alpha dot into this term, so on and so forth. Okay, you can represent. Now let's go to the third equation. That is the moment equation. Moment equation is fairly simple. There is not much derivation required, except we introduce a new term Cm alpha dot. Cm alpha dot is coming from Cl alpha dot. So you have an additional term. So this becomes square component comes here. Again, you can see that it depends on downwash. Downwash is the term that is time dependent. That is what changes your angle of attack at tail over time. So your Cm alpha dot will have the downwash component. Okay. Okay. Cm delta E we have studied before when we introduced elevators, control surfaces and all that. CMQ. Okay. So these are the questions of your week 10. So we'll just go over these questions. We will not solve them. Okay. So the first question is given. This is a second order ODE. So y double dash, so d square y by dt square minus y dash plus 6y equal to 0. And your initial conditions are given. What will be the value of y of t? So basically they've asked you to solve this ODE.
Yes, ma'am. Fine.
So I'm sorry about that. Okay, so this is basically they've asked you a question to solve a second order ODE. How do you proceed with it? You take y, assume y, the solution y of t to be e raised to at or something. Okay, so that is the solution. Now if you take differentiate it twice, so you have a square e of at. I'm just substituting this y of t into this equation. Okay, so you have a square y of e of at. Then you have minus 5 a square e of 80 plus 6 e of 80 equal to 0. Okay, so now you divide the entire equation by e of 80, you get a square plus 5a square plus 6 equal to 0. This is the characteristic equation. How do you proceed to solve this? I will not tell you the exact solution now because it's due tomorrow. So you take the roots of this equation, and the roots of the equation will basically feature here, right? E power at, the roots of this equation will be a1, a2. So you'll have two roots, and using the initial conditions, you can find out the constant. So final solution will be y is equal to c1 e power a1t plus c2 e power a2t. It will be of this form, or if you have repeated roots, something like that, you know how to solve differential equations. So substitute the initial conditions to find out c1, c2. Okay, we'll go to the next question. Next question, for the system shown below, find the value of damping ratio. So what is a typical second order system? How do you represent it? You represent it by s square plus 2 eta omega n s plus omega n square. Okay, so when you represent it this way, equate it to this. Eta is your damping, omega n is the natural frequency. You can find out omega n from here, and then you can find out eta from here. That is how you find out the damping ratio in this question. Okay, I will not solve it. We'll solve it in the next week. Okay, for the system shown in the figure, what is the time response for step input? Okay, how do you find out the time response for step inputs? Time response for any input. Step input, the Laplace transform is 1 by s. So R of s, the input is 1 by s. So basically what you have to do is find out the inverse Laplace transform of 1 by s into g of s. This is what you have to do to find out c of t. Okay, c of t is what is given in all these graphs. But a simple way, so when you solve it, the inverse Laplace transform 1 by s, you will get 1. So it will be something 1 plus or 1 minus, and then you have the solution of the typical ODE. How do you solve that? You know how to solve that. Okay, so that is how you do it. But a simple way to find out when the graphs are given, I'll just tell you. You take this equation, find out omega n, and then find out eta. How? S square plus 2 eta omega n s plus omega n square. Okay, so you can find out omega eta from there. Now when your eta is 0, that means there is no damping. If it's not damped, what happens? It will not come back to equilibrium. So it will oscillate about that. It is not damped. So this is the condition for that case. So it's a unit step input. So it will oscillate about that one value. Now if eta is, it's critically damped. Okay, if it's eta is equal to 1, eta is 1 is critically damped, right? Yeah. So if it's critically damped, then it will smoothly go to the desired value. Okay, it will not have any oscillations. It will go smoothly to the desired value of 1, that is input. Now if eta is less than 1, underdamped, it will go to the desired value and oscillate about it and finally come to the equilibrium. This is that case. Okay, underdamped. Now if eta is greater than 1, that is overdamped. So it goes fast to the desired point and it might overshoot. Okay, so this is that value. So these next set of questions, you can do it by analyzing the characteristic equation. You should ideally be solving this equation to find out the step response. But an easy way to check if your answers are right is this method. Okay, so you can do that for all these equations. Again, here the only thing that is changing is eta in all of these equations. Here eta is 0. Eta 0 was what? Undamped case. So what would be the option in this case? Okay, I'm not going to tell you the answer now. We'll discuss this next week, but this should help you solve this assignment. With this, we come to an end to our lectures, to our session. Is there any question? Do you have any questions? If not, I think we'll end this. It's already been very long. So we'll meet again next week. All the best for your assignment tomorrow. So I think I'll end this over here. Thank you.